Chapters 12 and 13 introduce a new type of elementary mechanism, reaction. It's called electrophilic addition. Now we've looked at each one of these elementary steps, and we have nucleophilic substitution, and we've got elimination reactions. And we've got these others, coordination where you form the bond, heterolysis where you break the bond, and the proton transfer. Now we're going to introduce pi bonds. Yeah, it's not there? Okay. Okay, let me write myself a reminder here. Yeah, I'll check it as soon as we finish this. Unless you want to take it while I'm doing my lecture. I'm just joking. Okay, so the concept still holds for reaction mechanisms. You've got an electron-rich reactant and electron-poor reactant. And in this case, the electron-rich reactant has the pi bond, has the double bond. And the electron-poor is, at least for this chapter, the electron-poor is the Bronsted acid. All right, so those are the topics. I mean, if you care about that kind of stuff, it's just there for educational purposes. Okay, when we consider the reactivity of a pi bond, we're looking at that extra electron density between the two nuclei. And we're using carbons as an example, but we've seen pi bonds with carbons with non-carbons like oxygen and nitrogen. And there are basically three reasons for its reactivity. And this has to do with the ability to break that pi bond. Now, the sigma bond is going to stay intact, right, because it's the stronger of the two. But the pi bond is, first of all, is electron rich, so it's going to attract an electrophile. And then also the pi bond electrons are not on axis between the carbons. They're out there they're more exposed, so to speak. They're off axis bonding electrons. And then when we look at the molecular orbital model for the pi and sigma bonds, we find that the pi bonds are higher energy than the sigma bonds. So that makes it easier to remove them. They're at a higher energy level, which means that they're closer to being broken than the sigma bonds are. Okay, so the reaction we're interested in for this chapter is, excuse me, electrophilic addition across that pi bond using a Bronsted acid. So the stronger the better. And the reason for that is the pi bonded molecule has the excess electrons, and the strong acid has the polar bond with hydrogen being electron deficient. Okay, so that's where the action happens first. In fact, that attack is the slow step. And what you end up with, this is overall reaction. We get the hydrogen is attached to one of the carbons, and what's left over, right? Oh, I didn't have my caffeine this morning. The conjugate base, in this case, the chloride ion, is then attached to the other carbon. So they don't both attach to the same carbon. The Bronsted acid is distributed hydrogen and conjugate base across that, what was the bond, the pi bond. Another example, sulfuric acid. You recall from your study in general chemistry, when polyatomic or polyprotic acids, sulfuric acid in this case, when they ionize, they do it one hydrogen at a time. Okay. So, since this is a strong acid, this is a weak conjugate base. Now, if we were to deprotonate that one again, which we could do in some reactions, then you'd end up with this proton and this sulfate. The only time this happens is usually when you titrate with a strong base. But we need a strong acid to accomplish this electrophilic addition. And that's not a strong acid. So this will not react. You only get this hydrogen off of that one, and the hydrogen sulfate is attached to the other carbon through one of the oxygens. Okay, so those are two examples, and this is a mechanism where we have electrophilic addition. Okay, so we got another one. I just listed the ones we covered so far. Now we've got electrophilic addition to add to our quiver. But the way we're studying the electrophilic addition here is with nonpolar pi bonds. You can have electrophilic addition across polar pi bonds, but that's a whole another couple of chapters, and we don't have time to do that one. Just so that you know it does exist. So the slow step, the rate determining step, is one where that nucleophile, which is the pi bond, attacks the hydrogen. And we get the addition of the hydrogen to one of the carbons, and both of the electrons from that pi bond are used to make the bond with the hydrogen. So you get a coordinated bond there because both of the electrons are donated from one side. And what that does is when that breaks that bond, that gives the other carbon a formal positive charge. Now that it's got the positive charge and the chloride ion is excess in electrons, it attacks that carbocation and coordinates a bond there. Okay. So technically speaking, that electrophilic addition is a combination of breaking the pi bond and coordinating the hydrogen with that carbon. But that is the slow step. And this is what it looks like in an energy diagram. The hill to get over the activation energy for that first step is relatively high. But then once we form the carbocation, we're at a dip. And then to get over the next hump is a very small amount of energy. So that's going to be a fast step, the coordination of chloride with a carbocation. And that makes sense because you've got a negative charge and a positive charge, in addition to the evidence for a small activation energy. All right. Overall, right, when we take all the mechanism steps included in electrophilic addition, the reactions are energetically quite favorable. And what we mean by that is in a thermodynamic sense. Let's go back. Notice that the products are at a lower energy level than the reactants. So what that means is this is an exothermic reaction, and that generally means favorability. Another way to look at it is you're adding two sigma bonds in place of one pi bond and a sigma bond. And two sigma bonds are generally stronger than, a sigma bond is stronger than a pi bond. That's true. So if we form two sigma bonds out of a pi and a sigma, then the overall balance is a stronger bond. And stronger bonding means more stability, lower energy, and favorability. So we can look at it two different ways. Okay, how about will alkene A or B react faster with hydrochloric acid? Well, let's see. The only difference I see, 1, 2, 3, 4, 5, 6, the okay. The difference here between the one we looked at already was a cycloalkene, just a simple cycloalkene. This has two substituted methyl groups on that alkene, on that cycloalkene. So what happens if, and it's got 1, 2, 3, oh, those carbons already have 4 bonds, don't they? There are no hydrogens. So that first step will never happen, right? 1, 2, 3, 4. Yeah, those carbons don't have any extra hydrogens. So B is the only one that's going to react anyway. Oh, I confused myself. And I saw some furrowed brows. You're probably wondering what I was talking about. The hydrogen doesn't come from the alkene. The hydrogen comes from the acid. Okay. So looking at it that way, the first step is the breaking the pi bond and forming a bond with the hydrogen. So both of them can accomplish that. But look at what is the result of this first step. You get a carbocation. Which carbocation is more stable? The cycloalkene carbocation is more stable because it's 1, 2, 3 tertiary. Okay, so that step should occur faster. That means the faster rate, the rate determining step, it favors the A molecule. I'm gonna have to go back and cut that other thing out. That was just a completely stupid statement. I don't know what I was thinking of. I wasn't thinking. That's the problem. Okay, so that's the rate determining step, and you should get the A molecule should react faster. All right. There are some cases where the electrophilic addition will not happen across a pi bond. And those are cases where you have very strong or heavy stabilization from delocalizing one pi bond with others. Now, the example we've got here is benzene, right? The benzene ring has all of those bonds in that benzene ring between the carbons, they are exactly the same. We write them as if there's a double bond and a single bond, but it's not that way. The bond lengths are exactly the same. The bond energies are the same. And that means that the electron density around between any two carbons is less because it's distributed among all 6 bonds. That, in addition to the fact that it's very, very stable, right? It would take a whole lot of energy, activation energy, to get that electrophilic addition to run, and typically it doesn't happen. So these Bronsted acid will not add to a benzene. All right. Oh, here's the explanation. It's resonance stabilized, right? Delocalized electrons around those 6 bonds. Now, if we had we could have 2 phenyl groups, attached to a double bonded carbon group in between. with the 1,2-diphenylethene, and we will get addition across that one. Acetic acid, I'm not sure why we add acetic acid in there, because acetic acid's weak. Maybe we're using acetic acid so that we don't get it may be, I wonder if it's on the next page. It may be that the acetic acid is being used as a proton transfer, an external I can't imagine why, though. Because hydrobromic acid is strong. Well, it's not quite as strong as hydrochloric acid. No, they're not going to show us. I think the only point to this slide is that the benzene is too stable, but that phenyl groups attached to that that double bond is still reactive enough. Okay. Now, how about regiochemistry? Which way do we get the insertion of the hydrogen and the chloride in this example? We have a propene, which has one terminal double bond, right? Should we get the hydrogen on the secondary carbon, or should we get it on the terminal carbon? Well, apparently the major product puts the hydrogen on the terminal. So we get a larger proportion of the 2-chloropropane than the 1-chloro. I mean, it's not a lot, but it's significant. And this happens with asymmetric alkenes. And notice that they have the same chemical formula, right? 1, 2, 3. So C3, H, 3, 4, 5, 6, H6, Cl. They have the same chemical formula, but they have different connectivities. So they're what's known, and we studied these earlier, of course, these are constitutional isomers. All right, let's see if we're going to get an explanation for why. Why is the major product the number 1 carbon substitution for the hydrogen, and the number 2 chloride substitution for number 2 substitution for the chlorine? If we look at it purely from a free energy standpoint, in order to get to the, well, actually, now that I look at it, it does make a lot of sense, right? If you pluck the hydrogen off of that number 2 carbon, what type of carbocation do you get? Right? You get a primary carbocation, because the positive carbon is primary. It's on the end of the molecule. But if you pluck the hydrogen off of the terminal carbon, then the carbocation is secondary and it's more stable. I think there's a name for this. Maybe it's on the next slide. So this regiochemistry says that the major product is going to be the conjugate base is going to be attached to the second carbon. No, didn't say. Oh, there it is. Yeah, Markovnikov's rule. And it simply says that the addition of a hydrogen halide of any kind to an alkene favors the product in which the proton adds to the alkene carbon that is bonded to the greater number of hydrogen atoms. And the example that we see there is 1-methylcyclohexene. We want the hydrogen to attack the number 2 carbon in that ring, so that the carbocation is on a tertiary carbon. That's the way I look at it. I mean, I'm sure that statement is true, but it just doesn't click with my brain. I'm looking for where is the most stable carbocation? And then the hydrogen attacks the other carbon. I mean, the hydrogen attaches to the other carbon. Excuse me. Okay. If that works for you, fine. If it doesn't, just memorize the rule. But you can probably guess already that there are anti-Markovnikov additions too. That's coming. But they should have perfectly logical reasons for doing it. All right. What's the major product of this addition? This is a molecule called endene. And it does have a benzene ring, so that's resonance stabilized. But there's a sigma bond to the south of the 5-carbon ring, and that breaks up the resonance stability. So that 5-carbon ring is not part of the resonance structure. We're going to cover that a little later. It's called aromaticity. The aromatic part of this molecule is in the 6-membered ring, the benzene ring. And the 5-membered ring is not part of that. So that 5-membered ring pi bond should be available. We just have to decide which way does the hydrogen and the chlorine add across that pi bond. All right. We've decided that that one is available. Right? So here are the two possibilities. If we add the hydrogen on the north end of that pi bond, then what type of carbocation do we get? We get a secondary carbocation. If we add across the other side, we get a secondary carbocation, but now it's 1 carbon closer to the resonance stabilized benzylic ring. That tends also to stabilize the carbocation. So if you the B situation is going to give us a more stable molecule, a more stable carbocation, which speeds up the reaction, and that favors the major product is going to be the chloride on the north end of that cyclopentane. So again, it goes back to the stability of the carbocation. Okay. Now, it is possible during one of these reactions for this to happen right here, carbocation rearrangement. Okay. That is entirely possible. Now, whether it's a 1,2 hydrogen shift or a 1,2 methyl shift depends on the molecule itself. In this case, it looks like the only option we have is 1,2 hydrogen shift. And if we add hydrochloric acid across that pi bond, we get the possibility for two different, well, initially, we have two different outcomes. We have the hydrogen on the terminal or we have the chloride on the terminal. Well, the problem is with the chloride, let's see. No, we're trying to stabilize the carbocation. Right, so the end product is going to be dependent on which one gives us the more stable carbocation. And if we you know what? If we add hydrogen on the terminal carbon, then that gives us a secondary carbocation. left over, and we could get some, the chloride would add there, but we could also get some products that are rearrangements. The carbocation then could shift by a 1,2 hydride shift over to the tertiary carbon, and then the chloride would attack there. We would coordinate with that tertiary. So the author tells us that we're going to get an equal amount, and the hydrogen is going to stay on that primary carbon. I think the reason for that is if we remove a hydrogen from the number 2 carbon, then we're going to get a primary carbocation, and that's very, very unstable. So the reaction that's preferred gives us the secondary carbocation first, and then some of those will rearrange to give you the tertiary. And that's why the hydrogen in both products is on the terminal carbon. And the chloride happens to be either on the second or the third carbon. And this is what the mechanism looks like. Okay, I guessed right. It was a 1,2 hydride shift that moved that carbocation to a tertiary position. All right, that's what it looks like as a picture. And it appears to have agreed with my verbal assessment. But it doesn't say anything about, I guess the author just assumes that we know that a primary carbocation is going to be too unstable. Now, if there are no other options, then you'll still get the chloride added to the terminal carbon, but it'll be a minor product. But since we do have this shift, then the reaction rates are so much faster for either the secondary or the tertiary carbocation that you get a mix of those products and none of the primary chloride. All right, what about this one? HBr. So we could add a hydrogen to the terminal, and that would give us a secondary, right? And then we would get a carbocation shift over to, let's see, my arrow, can you see my arrow? We would get a shift over to this carbon, which would be 1, 2, 3. Actually, it'd be a quaternary carbocation. Let's see if that's actually going to happen. I wonder if it is. Okay. All right. Oh, okay. My mistake. It's not a hydride shift. It's a methyl shift. Yeah. Because we can't make a carbocation. We can't make a quaternary carbocation. It doesn't work. So we have a 1,2 methyl shift instead. And that gives us a tertiary carbocation. So our products are going to have the bromide on the second carbon and on the third carbon, which is attached to the cyclohexane ring. Yeah. Okay. How about, that was regiochemistry. How about stereochemistry? Right. Remember, when we have double bonds, there's no chiral center on that double bond because you've only got 3 groups attached to it. And in order to have a chiral molecule, you have to have 4. But the reaction where you're going to add something across that double bond, the possibility for stereo center is possible. I just repeated myself. Overall, this particular reaction will give us a racemic mixture. Now, the hydrogen in the products, the hydrogen that's either sticking toward us or facing away from us, the wedge or the dash, that's the hydrogen that's already there. The hydrogen that we added is the blue one. It's kind of hard to see that color, but the blue one down below, that's the one we added. And when we did that, we formed a carbocation on the other carbon, right? And remember, the carbocation gives us a trigonal planar, an sp2 hybridized carbon. So that means the attack can come from the front or the back. And since there's no evidence of steric hindrance, I mean, it's whatever hindrance there is the same from the front or the back, then the bromine can be coordinated on the back side or the front side. And that gives you a racemic mixture, which means you should have equal 50-50 of the products of the let's see, are those enantiomers? Yes. You should have 50% of one enantiomer and 50% of the other enantiomer. Now there's possibility that you could add across a double bond and not get a not produce a chiral center. In order to do that, you would have to have some sort of symmetry about that carbon so that you have two of the groups on that carbon would be identical. If they're identical, then you don't have a chiral center. You have to have four unique groups attached to that carbon in order to make a chiral center. But in this case, we did end up with a chiral. Okay. So, what about this one where we have the 1,2-dimethyl cyclohexene? We've looked at it before, and we saw that the carbons are essentially equivalent. So you're going to get hydrogen on one side and bromine on the other. But look at what you get also, right? Just take one. Take that top carbon. You've got a hydrogen, you got a methyl group, and then you follow. Let me draw a picture for that. It'll help me talk about it too. So we had a cyclohexene, and now we have a methyl group and a hydrogen and bromine and another methyl group. And this is unique. This is unique. 1, 2, 3, 4, 5 with a bromine on it. So that one's unique. So we have 4 uniques this way and that way. So this is a chiral center. And if we start from this side, unique, all the way around. And that's a hydrogen and not a bromine. So this one is also a chiral center. So we have those two possibilities. And when the carbocation forms, the hydrogen can be added to either side of that double bond. Right? It could come in from the back side or the front side to form the bond with the hydrogen. And then the carbocation on the other one allows a front or a backside attack. So you get a combination of R's and S's. And remember from math class, right? How many possible combinations can you get from two unique, right? Like A and B. You can get an AA, you can get an AB, or you can get a BA, or you can get BB. So you can get 4 possibles out of that combination. I think that's right, combination. Combination is resampling, right? Permutation is not resampling. I'm trying to remember my math class. But we have 4 isomers, 4 isomers with the 2 chiral centers. out of this one reaction. Okay. Now, we're not going to go into any more detail about that because it just depends on uh, as far as which one is the majority. Well, I don't see any possibility for a majority. I would think that you have 25% of each one. But they won't all be enantiomers. Two of them will be enantiomers. You'll have two enantiomers, two enantiomer pairs, and then they will be diastereomers of each other. See what I mean? The RS will be, and SR are enantiomers, and the RR and the SS are enantiomers. But the RR and the RS are diastereomers. Okay, it can get confusing. Okay. Now I said earlier that you needed a strong acid to accomplish this, but since our reaction is rate limited, right? What can we do to change the rate? Add a catalyst. Okay. And a catalyst, it can come in many forms. Right? In this case, our catalyst, we're adding a weak acid, which is water. Right? Water is definitely a weak acid. Its pKa is only 14. So if we add a catalyst, a strong acid, then we end up adding across that bond hydrogen and a hydroxyl. Now, the question in my mind is, why don't we get a hydrogen and a sulfate across that? So I assume the next slide is going to tell us why. If you just try to add water to it, it won't happen. Reaction will not go, at least not in our lifetime. Okay, so here's what happens. The sulfuric acid protonates water molecule, makes a hydronium. Right? And in order to, you need an electron rich and an electron poor for that first step. If we have an acid acting as a catalyst in here, then we can protonate a water molecule and make it a hydronium. Now that makes it a stronger acid, strong enough acid. Right? So we've got a hydrogen in there that is electron deficient. In other words, the hydronium, if water is, let's look at it this way. This is for my benefit as well as yours. If we just look at water, pure water, and one of them is the acid, this is, and one of them is the base. Then we can transfer a proton to one, and we get hydroxyl plus a hydronium. Okay, so either one of these, weak acid, weak base. So this should be a strong conjugate base and a strong conjugate acid. Strong acid, strong base. Okay. So this is electron rich. It's not going to participate because we've already got an electron rich pi bond. We've got this molecule that has a hydrogen available for transfer. That's what the acid does. It causes that water to become a strong acid. Now that it's available, the pi electrons can attack it, can form a bond with hydrogen, form the carbocation, and then we get a coordination with what's left over, not just with the coordination then occurs with a water molecule. Right? And a water molecule is attached to the carbocation. And since the water molecule can accommodate the plus charge better than the carbon, it becomes positively charged. And now all you have to do is transfer that hydrogen to another water molecule, and you leave a hydroxyl behind. So the short story is the acid catalysis of sulfuric acid allows us to form a strong acid that's needed to conduct this reaction. This is called an acid catalyzed alkoxylation. Um, and oh, excuse me, my mistake. This is simply a acid catalyzed hydroxylation. The alkoxylation requires that instead of water, you use an alcohol. So instead of um, a hydroxyl attaching where the carbocation was, you're going to get a methyl ether at that point if it's methanol, or an ethyl ether if you use ethanol. But you still need the uh, added catalyze, the sulfuric acid, to catalyze the reaction, because you still have to produce a strong acid. You've got to protonate the oxygen on whatever molecule you use, and that makes the hydrogen available now for transfer. I thought we were going to get an explanation why the sulfuric acid doesn't interfere with that reaction. Because when we saw earlier, we had the sulfuric acid um, adding a hydrogen sulfide to the bond. Okay, the only way that can happen is if you don't have water there. So we must have used a non-protic solvent with sulfuric acid in it. That's the only thing that makes sense. Because if you have water, you're going to get this reaction where you add the hydroxyl instead of the hydrogen sulfate. Okay. Well, why is hydrogen chloride or hydrochloric acid not used to catalyze this reaction? Well, because hydrogen chloride, well, the only thing I can think of is hydrogen chloride would be preferred over a protonated water molecule. And instead of getting oxygen and hydroxyl, hydrogen and hydroxyl, you get hydrogen and chloride across that bond. Oh, here's our explanation. So we expect the hydrogen chloride in water to produce strong acid, which completely dissociates and protonates all these water molecules to hydroniums. And that 3 needs to be a subscript. It's not used to catalyze the reaction. If you want the hydration reaction to occur, it's not used because the chloride that's produced on the dissociation of water is a strong nucleophile and much stronger than hydrogen sulfate. So you get a competing reaction in there that, and since the carbocation is there, that means the stronger nucleophile is going to win. Right? So the chloride ion is a stronger nucleophile than the hydrogen sulfate ion. So that's why we don't use hydrochloric acid as a catalyst. My guess is that we could also use phosphoric acid. It might take a little longer, though, because the first proton in the phosphoric acid is also weak. So that probably wouldn't be a good choice unless you have some other extenuating circumstances. Sulfuric acid would probably be a better choice. Okay. Um, How about what happens to an alkyne? Right? Suppose we have hydrogen chloride in excess, and this reaction takes a while. Right? It takes a whole day. And I assume that we're at room temperature because it doesn't say heat anywhere. What the hydrogen chloride does to an alkyne, remember, you've got two sets of pi bonds there. Right? That's why you have a triple bond. You've got a sigma and two pi's. So one pi bond is going to give you a substitution, and then the other pi bond is going to give you another substitution. So you end up with what's called a geminal halide, geminal referring to twins. So you have chloride on the same carbon. Okay, and this is what it looks like. All right, the first step is the rate determining step, and we know that. Right, we've already seen that. That hydrogen bonds to the terminal carbon because that gives us a secondary carbocation. But the carbocation is vanillic, and vanillic is simply means that it's a double bond with the carbon, another carbon somewhere else. All right, so it's three carbons. Two of the carbons are sigma bonded together, and the other two carbons are bonded with sigma and a pi. That's a vanillic carbon. But this is a vanillic carbocation. And then the chloride will attack that one. It'll attack the secondary carbocation. Okay, what's left over? Well, you got a double bond there, right? So we add another hydrogen. Where's the hydrogen going to go? Well, the hydrogen is going to go where it will be most stable. Now, we would normally consider the secondary carbocation to be most stable, and it is stable, but it also is additionally stabilized with the chloride ion that's already there. So you get this resonance. That stabilizes the carbocation even further. So the second coordination of the chloride ion should occur a lot faster. But this is an explanation for why you get chlorides on the same carbon, is for the stability of that carbocation in both steps. All right. Well, let's see. So this is what we would expect if we had propine and we added hydrobromic acid. It takes a little longer because hydrobromic acid is a weaker acid than hydrochloric acid. So we know that we're going to get a 2,2-dibromo propane after about 4 days. And in this case, they're saying that we don't get resonance stabilization. A pi complex of acid with the alkyne. All right. So that's different. The difference there is the chloride versus the bromide. And I think the reason for that is that the hydrogen bromide is a weaker Bronsted acid. So instead of, we get an association there. Well, no, that's just another way of saying we get the bond is formed with the hydrogen. No, there's no difference there. It's just another way of showing it with the curved arrows, right? So we're doing that as a concerted step, when in fact it's probably separate steps. But we still end up with the same product. And now with that bromide, same carbon atom. And then the bromide, well, they're leaving us hanging, right? There must have been something else that needed to go in here, because we're supposed to get a dibromide, a 2,2-dibromo anyway. Yeah, for the same reasons. Okay, so I don't see any difference between the chloride and the bromide. Unless you do. Does anybody see a difference there? No, I don't see a difference. The only difference I see is the length of time, like 1 day versus 4 days. Okay. So what about an acid catalyzed hydration of an alkyne? Um, so what would that give us? Well, when it was an alkene, we got an alcohol. But with an alkyne, you get a ketone, acid catalyzed. Now, this one has to occur at higher temperature. So that tells me that the rate determining step is too slow for room temperature, even catalyzed. So we have to increase the temperature. We're going to end up with an alkene, a ketone, where the oxygen is attached to the, not the terminal carbon, but the second carbon. And let's see what that looks like. All right, so we've got our hydronium ion, right? We've seen that step before, right? We form a bond with the hydrogen, and that releases the water molecule and makes a carbocation on the second carbon. Okay, then we coordinate a water molecule, yes, with that carbocation, and that leaves a hydroxyl. That's the enol. But the enol tautomerizes with the ketone because the ketone is more stable. Right? I think we looked at that earlier. The keto form is more stable. So when that happens, and this, let's see. Yes, the curved arrow goes from the pi bond and goes to the carbon oxygen bond, and that leaves behind a let's see, what does that do? I got to draw. Back to the board. Trying to make sense of this one. Okay, so we've got this phenyl group, right? And then we've got this carbon and this one, which at this stage we have a double bond there and OH there. So that's the enol with a hydrogen here. Now, is that the only hydrogen we have? One, two, three. There's another hydrogen there. We're only showing one of them. Okay. So how does it tautomerize? This the electrons from this double bond go here. That means that now we're deficient, right? We move those electrons there to make that double bond. This becomes deficient. Yeah, they skipped a step. I mean, they put 2 steps. Well, that's why they have 2 arrows. Right. So what we end up here is like this and this and that. Let's see, 1, 2. That can't be. So what we have here is formal charge on oxygen. It's 6 minus 1, 2, 3, 4, 5 minus 5 equals 1. So this is a plus, and this becomes minus. Right? Oh, no, that's a minus. Excuse me. This is electrons, 5 electrons. This is a -1 because this is minus, and this is 5 others. Okay, so that's minus, and this is a plus. So now our carbocation is here, and the keto is more stable, so it has to get rid of this hydrogen. It gets rid of one of the hydrogens. And that hydrogen is transferred to a water molecule. All right, now that makes sense to me. That's why we get a ketone, because the keto form is more stable than the enol form, and that's accomplished through proton transfer. Actually, there should have been four. It should have been. Oh, I forgot to get rid of this one too. Now this one is neutral. Okay. Now I made sense to myself. Did that make sense to any of you? Because there's always a risk. A lot of the stuff that I'm doing up there is occurring in my head and it's not coming out where the class can hear it. Okay. So here's that mechanism again. And we're going to talk about it. The product of step 3 is an enol. That's right. Okay. Under acidic conditions, the enol rapidly tautomerizes to more stable keto form in 2 steps. And hopefully I showed that. Which are both proton transfers. Yeah. Okay. All right. 2 important aspects of this reaction. The product is ketone, not an aldehyde. An aldehyde would have to be on a terminal carbon. The ketone, the oxygen has to be double bonded to a carbon with a secondary carbon. Let's put it that way. The oxygen bounded to a secondary carbon is a ketone. Oxygen bounded to a primary carbon is a aldehyde. And this does not form an aldehyde. We have to run the reaction at very high temperature. The intermediate, the first intermediate that's produced, that vanillic carbocation, is unstable. So the first step has a very large energy barrier when the hydronium ion is the acid. And that can be surmounted with a large amount of added heat. All right. How do we increase the yield of an acid catalyzed hydration? You may not have to do this every time. It's only when the yield is, you're expecting the yield to be low, that you need to approach the problem in such a way that you increase the yield. And these are techniques that you can use. Ethynyl benzene. Okay. Well, we need actually, in order to increase the yield, you need a stronger acid than the hydronium ion. You need a stronger catalyst. So this one is, what is that abbreviation? I can't remember. We had it before. TFOH. You know, I think that molecule below is showing us what it is right here. Trifluoroethanol. Oh, that's it, right? It's trifluoroethanol, abbreviated TFOH. Okay. So that is a stronger acid. And it's a stronger acid probably because of the fluoride electron withdrawing effect. It draws electrons away from the next door carbon, which again draws electrons away from the oxygen, which draws them away from the hydrogen, and makes that hydrogen more acidic than even sulfuric acid. Okay, and then we increase the yield. We get the same product. It just happens, probably happens at a lower temperature and with a higher yield. Um, yeah, without extreme temperatures, if the acid conditions are stronger than hydronium. Trifluoromethane sulfonic acid. Well, that's different. Also known as triflic acid. Okay, my mistake. So the solvent is 2,2-trifluoroethanol. 2,2-trifluoroethanol. And the catalyst is triflic acid, trifluoromethane sulfonic acid, which is a much stronger acid than sulfuric. We saw that as I think as a leaving group in the past, didn't we? Triflic acid. I thought that was a good leaving group. Okay, how about electrophilic additions to a conjugated diene? 1,2 addition and 1,4 addition. Okay, what do we mean? We haven't talked about conjugation yet, have we? Or did I mention it already? Here's what you look for in a conjugated system. Simplest one I can think of is this 1, 2, 3, 4 is bute, 1, 2, 1, 2, bute, 1, 2, diene. Okay, that's the simplest conjugated system I can think of. Anytime you have a double bond, a carbon chain with a double bond, a single, and a double, you get conjugation, a delocalization of the electron density over this entire system, which stabilizes it. This is a more stable system. Oh, I should have just looked at the slide. It's not 1, 2, it's 1, 3. That's what the puzzled look was. Right, Galen? So, when you have a conjugated system like this, it's still electron rich, very electron rich. It does undergo electrophilic addition from a strong Bronsted acid, but we get two different products. We get one of the chlorines is on a secondary carbon, and the other chlorine is on a primary carbon. But there's a double bond remaining. I can't help but think that something else is going to happen with that other double bond. So there's probably more coming. You could possibly get one of you get both of these products. All right. The double bond on the first product, 3-chlorobutene, it remains in the same place. The double bond on the 1-chlorobutene has moved. It's shifted from the terminal carbons to two internal carbons. And the product, the 3-chlorobutene, is known as a 1,2 addition. That just means the hydrogen and the chlorine are added to the first and the second carbons. That's a 1,2 addition. The other product is a 1,4 addition, where the hydrogen is added to terminal carbon, but the chlorine is added to the other terminal carbon, number 4 position. Right? In this case, it's a terminal carbon, but if the molecule were longer, it would simply be the 1,4 position, separated by 4 carbon atoms. Okay, so here's what happens. The acid the proton will be attacked by the nucleophile, the electron-rich species, the but-1,3-diene, and you still get that proton transfer. Where is it going to go? Typically, it goes on the primary carbon because the carbocation, the secondary carbocation, is more stable. But you can also resonate. Resonance stabilization will also give you some primary carbocation resonated with that secondary carbocation. And that makes both of them available for attack. So you can get both the 1,2 addition and the 1,4 addition. And the resonance hybrid is shown at the bottom. That's what actually looks like, right, where you have those dashed lines. And each of the carbons, the 2 and the 4 carbons, have a partial positive charge. So you can get an attack at either position, either the 2 or the 4. Now, my guess is that even though that's stabilized, you should get a predominance of the 1,2 addition. Now, let's see if that's true. Let's see. Okay. Both conjugation and resonance stabilization of the carbocations cause the intermediate products to be produced. Now, the product that won't be produced is a terminal alkene with a primary carbocation. That's not stabilized. Notice that the carbocation is 2 carbons away from the double bond. So you can't get resonance stabilization with that one. It's only when the double bond is 1 carbon away. The carbocation is 1 carbon away from the double bond. Then you get resonance stabilization. Okay. So here we go again with kinetic versus thermodynamic control in electrophilic additions. And this is valuable, a discussion in terms of the conjugated dienes. So at high temperatures, electrophilic addition to a conjugated diene is reversible. Okay. All right. So look at where the products are in relation to the reactants, right? We're still in overall exothermic reaction. At high temperature, you've got enough energy to drive the reaction reversibly, right? You can meet the activation energy in the reverse direction. So if you can go both ways, that's thermodynamic. Reversible reactions favor thermodynamic control. So that means that the major product is the one at the lower energy. At low temperatures, you don't have enough energy to go back in the reverse direction. So that at low temperatures, the reaction is under kinetic control. It's irreversible. And the major product is the one that is produced the fastest. Okay, that being said, which one is which? The thermodynamic product of the electrophilic addition is generally the one that in which the remaining carbon-carbon bond, carbon-carbon double bond is the most highly alkyl substituted. Right? So the 1,4 molecule is more stable. The alkene is more stable. Whereas the terminal alkene, the 1,2, is less stable. Right? So the thermodynamic control is going to be the one that is the more stable. Thermodynamic control will give you the B product, the 1,4 addition. And that means it has to occur at higher temperatures. All right, so you're going to get the terminal chlorine on this molecule under high temperatures. Under low temperature, you're going to get, probably on the next slide. No. Under low temperatures, you should get the 1,2 because it forms faster. All right. So this is what it looks like at room temperature. Let me see if this explanation helps. The but-1,3-diene is carried out at room temperature, then the 1,4 adduct is the major product. 20 degrees is considered, it's considered high temperature thermodynamic control. All right. As Einstein would say, it's all relative. So we're saying, all right, 20 degrees C is a high temperature. Under what circumstances? Well, if you change it to K, right? 293 K, that's a high temperature. So I guess it's relative. I mean, you have to decide for each reaction what is considered high temperature and low temperature. So if you wanted the 3-chlorobutanene, then you would have to conduct this reaction on ice, right? You have to make it cold. And that tells me that it's probably going to take a while for you to get a product. So you may want to look around for a different way to end up with that product than this particular reaction. If you want the 1-chlorobutanene, then yeah, just go ahead with it and you'll get mostly. And my guess is if you increase the temperature even further, say 40 degrees, that the proportion would be even higher for the 1,4 product. There you go, minus 80 degrees. How are you going to get minus 80 degrees C? Do you have to put it in a freezer? I guess that's possible. I used to work with ultra low temperature freezers that would go down to minus 100. You could do that. You could get close to it with dry ice. Dry ice is minus 78, right? So maybe that would work. And then the product would be the one under kinetic control because of the low temperature. All right. So I was right all along. It's just that their idea of a high temperature was different than my idea of a high temperature. Okay. So we're going to beat this horse some more. 1,2 adduct is the kinetic product because of where chloride is located after completion of the first step of the mechanism. Upon addition of the hydrogen to the diene, chloride is closer to the C2 than it is to the C4. Okay. And you still get stabilization from a secondary carbon rather than from a, well, not, that is a secondary carbon rather than a primary carbon. Yeah. Right. You get stabilization there. And they've carried out this step. Actually, there are two steps with the curved arrows. You see, there are two steps going on there. Right. The hydrogen, the proton transfer and the coordination bond, and then the chloride attacks. So they've conflated two additions there to end up with a 1,2 adduct, and that happens faster, much faster than the 1,4 addition at low temperature. Okay. So if we look at this in terms of a retro synthesis scenario, if you knew that the product you wanted was the bromine substituted, then you could work your way back to the carbon-carbon double bond in between those phenyl groups. Could we also do that for if we wanted a alcohol or an ether in that bottom example? Undo the addition of water or ROH. We started with a terminal alkene. Would that work? Well, apparently it does. If we wanted a geminal dihalide, right, then we could work with an alkyne. If we wanted a ketone, we would go with a actually, it depends on where that middle one, it depends on where that alkyne is located, right? If it's a terminal alkyne, you're going to get a ketone with a methyl on one side and the rest of the molecule on the other. But in this case, we've already got a methyl. And now when we form the ketone, we have an ethyl group on one side of the ketone and a phenyl group on the other side. How about that bottom one? Allylic halide. That one is strange to me. I wonder if they're going to work those out for us. Nope, they're not. Okay. Would that work, though? I mean, if you wanted that cycloalkene, yeah, that cyclohexene, cyclohex-1-ene with a 1, 2, 3. Would that be 3-chloro? Yeah. 3-chloro, 1-methyl, cyclohex-1-ene. Or just cyclohexene. Yeah, 1-ene would be redundant. So if we wanted that one, we would have to substitute the chlorine. Would that work? Oh, okay. I see what's happening. You're going to get a methyl shift from the number 1 carbon and leave behind a more stable. You're going to work from a conjugated system, right? See that double bond, single bond, double bond. That's conjugated, right? So what that's going to give us is, under the correct conditions, what that's going to give us is the allylic halide that we desire. But would that be a 1,2 or 1,4 addition? That would be a 1,4, right? So that would have to take place at high temperature. All right, how about this one? We've got a terminal bromide, and we want to terminal bromide, 1, 2, 3, still have 2 carbons on the outside, but we've created a carbon bond. Okay, that's going to take more than one step, I think. Is there a carbon bond formed? Yes. Okay. What precursor could the halide be formed, and can the alkene be produced from the starting materials? How do we write the final synthesis? Okay. So we want to end up with that cyano compound. If we start with the bromine in that place and then attack it with a cyanide, we get a SN2 reaction. We get a substitution, right? Then how do we get the bromide? Well, if we have an alkene, then we can end up with the bromide on the secondary carbon. That would work. Yeah. So then if we write it out as a synthesis, wait a minute. We're not finished yet. Sorry. Right. We got the alkene for the proper bromide, but we have to make the alkene from an elimination reaction. Then if we put them in the correct order, right? We start off with that terminal bromide, and then we have to hit it with a very strong base. Tertiary butoxide would be a good one. And that would form the double bond. The bromine would be a leaving group. And then we'd hit it with a hydrogen bromide. And hydrobromic acid. Then we could put the bromine in there, and then we substitute the cyanide. So that would be the sequence. I mean, it makes sense when you see it that way. Terpenes and their biosynthesis. So what's a terpene? Well, terpenes were initially isolated from natural products. And those that are related to them, terpenoids, include groups of the steroids and other essential oils. So the steroids are a much more complicated or complex terpene, but they fall into the same family. It consists of isoprene units linked by their terminal carbons. Okay, an isoprene unit is always 5 carbons. 1, 2, 3, 4, 5. And it's an iso version. Remember, anytime you have an alkane, if you move one of those carbons to an internal carbon as a branch, that's an iso. So this is an isoprene unit where you have 1, 2, 3. Actually, it's a simplest form of an isoprene is that one at the bottom, 2-methyl-buta-1,3-diene. And notice those double bonds are conjugated. That's important for any further reactions to occur. Okay, these are examples, and we've drawn shaded parts of the molecule to show you where the isoprene units are located. Right there, they're always 5 carbons together to make the isoprene units. So pine resin, alpha pinene, limonene, right, from citrus fruits, ginger oil, zingaberine. It's a more complicated molecule. And then I'm not sure about this sembrine A from corals. That's a new one on me. Squalene, I'm familiar with that one. You'll get introduced to that one again if you take biochemistry. So that's 1, 2, 3, 4, 5, 6 isoprene units linked together. And notice the isoprene units have the previous page where we had 2-methyl-but-1,3-diene. Those are conjugated, but notice that the double bond moved internally, and the other 2 double bonds are gone. There's only 1 double bond left now for the formation of that the connection of one isoprene to the other one. So squalene probably comes under the heading of polymers. That would be my guess, because it's repeating units. How do we classify terpenes? Well, it depends on how many pairs of isoprene units. If you have 1 isoprene, it's a mono. You can have a sesquiterpene. The difference there is that the number of isoprene units for a mono is 2, but the number of isoprene units for the sesquiterpene is 3. I need some examples, don't you? Yeah, I need some examples. So what would menthol, geraniol, and retinol? Oh, that one. Look at all those conjugated double bonds. I bet that's a colored molecule. I bet you can see that one. Yeah, I bet you can actually. The more conjugated double bonds you have, the lower, the redder the color. Let's put it that way. Okay. So if you have large numbers, like if you have, I think 30 carbons in the conjugated system, in the carotenoids. You get the orange color for carrots. You get the red color for lobsters and crawfish. They have the conjugated system. And the more conjugated bonds you have, the redder the color. Let me see. So the monoterpene, the number of pairs of isoprene units is 1. The number of isoprene units is 2. So 1 pair with 2 isoprene units. That makes sense. The number of carbons then would be 10 because each isoprene has 5 carbons. Okay. But sesquiterpene says the number of pairs of isoprene units is 1, but the number of isoprene units is 3. I'm not sure how you get that with 15 carbons. Diterpenes have 2 pairs or 4 isoprene units and 20 carbons. Okay, sesquiterpene is the one that gets me confused. The rest of them make perfect sense. So let's see. We got 1, 2 for menthol. We got 1, 2, 3. Which way do we go? 1, 2, 3, 4, 5, and 1, 2, 3, 4. That's only 4. So menthol, you may see an isoprene unit in there, but it's not enough to make 2 of them. Wait a minute. Yes, it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, there are 2 isoprene units in there. How about geraniol? 1, 2, 3, 4, 5, and the 1, 2, 3, 4, 5. Okay, geraniol's a number of pairs. 1 pair is a monoterpene. How about retinol? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So you got 20. That means you've got a diterpene there. Number of isoprene units is 4 with 2 pairs. Okay. I think that's all I can get out of that. How about isopentenyl diphosphate? If we start with acetic acid and we keep bonding acetic acids together, we can get potentially mevalonic acid. And this is probably under enzyme control. That's what I'm thinking. I would be hard pressed to make that. We could make it with a pure inorganic, not inorganic, non-biochemical means. And then we want to add phosphates. Now, why would we want to add phosphate groups to that molecule? Anybody been introduced to this concept in biology? Phosphates added to molecules tend to activate them so that they can enter into certain reactions. Just think of ATP, adenosine triphosphate. It's a very high energy molecule. It's like the base currency of energy in the cell. And when you remove one of those phosphates, it gives up that energy of the bond. And then it also participates in various reactions because of that high energy state. It activates certain molecules so that they can enter into enzymatic biochemical reactions. How do we make the dimethyl allyl diphosphate? Right? Isn't that what this one is? Yeah. Aha, enzyme. There's an enzyme that's going to do a proton transfer to that double bond. And when it does, it makes the carbocation, the tertiary carbocation, and then the tertiary carbocation under the influence of another, that's electrophilic addition. So we've added, okay, we've added a hydrogen. And then the enzyme, this may not be the same enzyme, but okay, it should be, right? Because uh, we've removed the hydrogen, left the electrons behind. So that's the same enzyme. Okay, now it takes a proton and recreates the double bond on neighboring carbon, dimethyl allyl diphosphate. So what we're saying is that this reaction will not proceed unless those diphosphates are attached. That's the way I read it. Okay. All right. So the takeaway from this particular reaction, the synthesis of terpenes involves reactions through the carbocation intermediates. Right. And this carbocation is made possible by two features of the diphosphate molecule. One is the carbon-carbon double bond. We know that's there. And the diphosphate group, which is a good leaving group. It has a good leaving group ability. All right, now that second one doesn't make any sense to me because it didn't leave, did it? My thinking is that you attach the diphosphate there to facilitate the reaction with an enzyme because enzymes are very particular about the substrate that they attack. So that phosphate has to be there. But once the phosphate has done its job, then it can leave. And like I've said so many times before, that's the only thing that makes sense to me. First step is electrophilic addition. We saw that. Okay. Second step is elimination of a proton. And the more stable carbocation intermediate is produced. And this one adheres to the Markovnikov's rule. Okay. Giving you the more stable carbocation intermediate. Yep. And the substituted alkene product, the more substituted alkene product, obeys Zaitsev's rule also. We haven't heard from Zaitsev in a little while. All right. So this is a detailed mechanism, right? That was an overall mechanism. This is a more detailed mechanism. Let's see. Oh, we're completing the reaction, right? Well, if we have the dimethyl allyl diphosphate that we produced in the previous, yeah, on this slide. Okay, so we're picking up where we left off. Now that diphosphate is a good leaving group, it leaves behind a carbocation, a terminal carbocation. And the only reason it can do that, I think, is because it's resonance stabilized with that double bond. Right? Normally, primary carbocations are not very stable. And then we have an electrophilic addition because now we have a carbocation with a pi bond that can attack it. And that forms the connection of the two isoprene groups. And that can continue, right? Because now you have another leaving group on the end of your molecule that can leave and regenerate another carbocation after the double bond is formed. Right? We still have to form that double bond. And then now you can continue. You can have another reaction. All right. Heterolysis, okay. That's just describing what happened each time. Now we have 10 carbon atoms. Okay. Elimination of hydrogen produces geranyl diphosphate and neryl diphosphate. Oh, okay. You can get, you could either get an E isomer or a Z isomer out of this. Same number of carbons, they're just isomers of one another. Right, so those are two possibilities. And then I can imagine that the polymerization can continue. In other words, you can go through the same heterolysis as before and then connect with some other molecules. This could get complex. You could have a messy mixture pretty quick with this reaction because it produces two different products. And then the carbocation can interact with any of those products, or it could interact with another isopentenyl diphosphate. So you could get really messy in a hurry. I wouldn't want to have to make sense of this reaction or produce a certain product. Yeah. Okay. All right. These are examples of producing natural products like limonene, geraniol, and I'm not going to go into a lot of detail with those. They just undergo reactions similarly to the previous one, where the diphosphate is a good leaving group. And that's enough for chapter 12.